Okay, so the next talk will be from Alexander Bagnall. I don't know if I pronounced correctly, on the topic of formally verified samplers from probabilistic programs with loops and conditioning. Go ahead.
Okay, hello? Okay. All right, so thanks for the introduction. I'm Alex, and this is joint work with Gordon Stewart and Anindya Banerjee. So this talk is really about a verified compiler for probabilistic programs. So I think it can be helpful to understand what's going on by analogy to verified compilation of conventional programs, where the verified compiler is really one part of kind of a bigger picture of program verification, where formal reasoning on the source program can be composed with semantic preservation of a verified compiler, for example, CompSert for C programs, to obtain formal guarantees on the output of the compiler, for example, verified assembly programs. And there's something similar going on here in the probabilistic setting, where instead of C, we have a probabilistic programming language called the cpGCL, and it has a formal semantics called CWP. These are taken from existing literature, and I'll explain them a little bit more in a bit. And so formal probabilistic reasoning at the source level can be composed with the semantic preservation of our compiler that we implement here. It's called ZAR, to obtain formal guarantees on the output of compilation, which is not an assembly program, but a sampler. And the sampler is basically just a function from uniform randomness, some source of uniform randomness, to output samples. And the ultimate kind of formal guarantee we obtain is this thing that we call equidistribution, which says that if the source of randomness really is uniform, then the output samples will be equidistributed with respect to the CWP semantics of the source program. So this work is really about the bottom two-thirds of this diagram on the right, about the verified compiler and the equidistribution theorem, and not so much about using CWP to verify individual probabilistic programs. Okay, and now just to kind of motivate why we care about verifying sampling, we can look at a little example really quickly. And this example is fairly common in the real world, so you may have seen it before. We have a C function called uniform. It takes an integer argument n and returns rand mod n. Rand is from the standard library. It just generates a pseudorandom integer uniformly from the range 0 to random max, where random max is some large power of 2. Suppose that that's really true. Then the idea is that uniform of n should generate a pseudorandom integer uniformly from the range 0 to n. But, of course, it doesn't quite work out that way. Suppose rand max is 2 to the 16, for example, and n equals 5. We would expect to see the output distribution of uniform of 5 be something like this figure on the left, but in reality, it's more like the thing on the right, where there's a slight bias toward the lower end of the range. And this figure is exaggerated a bit. In reality, the bias is so tiny you can't really see it, but it's there. Okay, this is called modulo bias, because it arises due to the use of the modulus operator when n does not divide evenly into rand max. And the really nasty thing about bugs like this is that not only are they very common, they can be really difficult to detect, and they're kind of lurking about, and you don't really know. And testing doesn't really help you very much. So what we really want are a priori guarantees on the absence of bias or correctness of sampling in general. And so that's why formal verification is useful. Okay, so this talk is about ZAR. It's a probabilistic programming language compiler that is implemented and verified in Coq. The probabilistic programming language that it supports is the cpGCL, which stands for Conditional Probabilistic Guarded Command Language. It's a core probabilistic programming language that includes probabilistic choice, basically flipping a biased coin, loops, and conditioning, which makes it useful for encoding Bayesian models. ZAR compiles cpGCL programs to samplers where all of the probabilistic choices are reduced to fair coin flipping schemes. So this is kind of a key idea of how the compiler works. Or in other words, to samplers in the random bit model, where the random bit model is kind of the simplest execution model for samplers, where the sampler is provided a stream of uniformly distributed random bits that it can consume to produce its output. Okay. Here's an example cpGCL program. It's called primes, and it takes a rational parameter p. On the first line, we see the syntax for probabilistic choice. You should read this as, execute the code in the left-hand side with probability p, or the right-hand side with probability 1 minus p. So this line is basically just flipping a coin with bias p and storing the result in variable b. Then we have a loop that repeatedly flips the coin, keeping track of the number of heads, if we consider true to be heads, in this counter variable h. And so, this program is just kind of flipping a coin and counting the number of heads and then terminating as soon as it flips tails. If you think of it that way. And then at the end, we observe h is prime. So this has the effect of ruling out all executions of the program for which h is not prime at the end. And so a sampler for this program will only produce program states in which h is prime. Okay, we can take this program and feed it through the Zark compiler to obtain a sampler in the random bit model that can be represented graphically like this. And then correctness of sampling, or of compilation, is twofold. The first part is just kind of a regular old notion of semantic preservation, where we define a formal expected value semantics on the sampler representation and show that it agrees with the CWP semantics of the source program under compilation. But then we go a step further to kind of push the semantic preservation through to the actual samples that are generated with the equidistribution theorem. And this says that if you take the sampler and use it to generate samples, then eventually any subset of the sample space will get its proper share of samples in the long run, where proper share is defined as the probability of the subset according to the semantics of the source program. Okay. So here's a diagram of the overall ZAR architecture, the compiler pipeline, and it's not too complicated, so we'll be able to focus in on each of the major parts in the following slides. But just to give a brief overview, we start with a formalization of the source language, cpGCL and its CWP semantics, which I'll explain in the next slide. And then there's an intermediate representation called choice fixed trees. And then there's a debiasing transformation on that intermediate representation. And this is where the reduction of bias choices, this is where we kind of drop down to the random bit model. So this is a critical part of the pipeline. And then for the purposes of execution, we target a coinductive representation. And for that, we use the existing interaction trees library that was introduced at POPL a few years ago. Then we prove the equidistribution theorem through a bit of a detour. There's a little auxiliary proof framework that we use here to make that happen. And then we have some empirical results on extracted samplers. Okay, so the source language, it's the cpGCL. We've seen it already. Then the semantics is the CWP semantics, which stands for conditional weakest pre-expectation. It's sort of like weakest precondition semantics, but generalized from predicates to expectations, where an expectation is a real valued function on program states. And so, in a nutshell, CWP is an expected value semantics. It can be used to answer questions like, what's the expected value of this function over all possible executions of a program? And as a special case of expected values, it defines probabilities of events, where events are just sets of states. So the probability of event Q is the expected value of the characteristic function for the set. Okay, then the first step of the compiler pipeline is to take the program and a given initial state and to kind of specialize the program to the initial state to encode all possible execution paths, kind of random executions in a tree-like data structure where there's a branch in the tree for every probabilistic choice, and there are these fixed nodes for encoding loops. Okay, so then why do we need this representation? Well, the main reason is to enable the debiasing transformation. Because at the source level, the probabilistic choices can be biased, and to arrive in the random bit model, we at some point need to eliminate those biased choices and replace them with semantically equivalent constructions containing only unbiased choices. And we can't really do this at the source level as a source-to-source translation because the probabilities there are expressions that can depend on the state. But in the choice fixed tree representation, we've specialized to an initial state and kind of propagated that throughout. And so all the probabilities appearing in the tree are constant. And so it's a convenient place to do this transformation. So that brings us to the debiasing transformation as the next step in the pipeline. And here's an example of what it looks like. On the left, we have a biased choice with bias 2/3. And it gets transformed to this thing on the right, which is a little bit more complicated and involves a loop even. But all of the choices are unbiased. They have bias 1/2. So there's a generic algorithm for doing this. We proved that it preserves semantics by a geometric series argument. And so then at that point, we have debiased choice fixed trees, and those can be considered already an encoding of samplers in the random bit model. And so now we want to be able to execute them. But there's a problem, and the problem is loops. So these could be loops from the source program or loops that are introduced by debiasing. But the funny thing about these loops is that like even in this example here, this is a loop that terminates with probability 1, but it's only sort of probabilistically terminating. It's not absolutely terminating. So no finite upper bound can be placed on the number of iterations that are required to terminate. And you can't get away with some trick using fuel because no amount of fuel will ever be sufficient to guarantee termination. So we can't really get around this problem of potentially infinite executions. So we need a coinductive representation. So that's the final step in the pipeline. And it's conceptually pretty straightforward here. We are just kind of taking the unrollings of all the loops, kind of taking their infinite expansions to arrive at these potentially infinite trees. And those are our encodings of the random bit samplers that we can extract and execute. Okay, so now that's the compiler. Those are the implementation steps. And now we need to prove that it's correct. The first part is semantics preservation. And so to do that, we need an analog of CWP at the level of the interaction tree coinductive samplers. And that turns out to be a little bit awkward because, well, typically you would define it by induction on the structure of the trees. But coinductive types don't have any induction principles. So to work around this, we devised a little proof framework based on the notion of algebraic CPOs, where we define the semantics by induction on finite approximations and continuously extend it to the coinductive type. So we have a little framework for defining and reasoning about continuous extensions on algebraic CPOs. And so that all works out. And so we eventually get our semantics on the I-tree samplers, and we can prove that the whole pipeline preserves the semantics. Okay? So now we're almost done, but we still have to prove the equidistribution theorem. And it's also proved using this auxiliary framework. And the equidistribution theorem basically just says that, well, assuming that the random bits provided by the environment are indeed uniformly distributed, then we have equidistribution, that for any event, any subset of the sample space, the proportion of samples that fall within the event converges to its probability, where the probability is defined as the expected value of its characteristic function according to CWP semantics of the source program. And so this, the equidistribution theorem kind of reduces our assumptions to sort of a minimal thing, that as long as the random bits are uniformly distributed, then the samplers will be correct. Okay? And then we do some extraction to OCaml and some experimental validation on samplers. And I don't really have time to go into details here. The analysis is done in the paper. But the gist is that, sometimes the performance is quite good, but in some cases it's not. And in particular, when the source program conditions on low probability observations, then that can really degrade the performance of the samplers. And in the special case of uniform sampling, which is related to that modulo bias from the introduction, we extract some verified uniform samplers that have no modulo bias, of course, no bias at all, and we compare performance with some other well-known samplers from the literature, the fast-loaded dice roller, an optimal approximate sampler, and show competitive performance. We provide some Python 3 wrapper code for calling verified samplers from Python code. And there's also an OCaml package that is on OPAM that takes it a little bit further. It kind of came out of this work that I think is pretty neat. So you can check that out if you're interested in doing verified sampling in OCaml. And so just take away, we formalize cpGCL and CWP. We compile all the way to I-tree coinductive based samplers. We do it through this choice fixed tree intermediate representation, and we ultimately prove equidistribution of the resulting samples. So that's it. Ready to take questions. Sure. Okay. Yeah, so the looping is an essential part of that. Whoops. Yeah, so he said, how does debiasing work for probabilities that don't involve a power of 2? I think that was his question. And the essence to that is that we can introduce loops. So basically, the probability is always rational. And what you can do is if the denominator is not a power of 2, you kind of just choose the next power of 2 that's greater than or equal to it. And you can kind of build the tree using that power of 2. And then any of that overflow can just loop back to the beginning. You basically implement a rejection sampler using a power of 2 construction as the basis. So I don't really have time, I guess, to explain how it works exactly, but we can take it offline if you're interested.
Okay, that makes sense. Yeah, and I was just wondering, in general, like there's lots of crazy ways to sample from probabilistic programs like sequential Monte Carlo and MCMC. How far do you think we can push this in terms of getting verified implementations of these?
Okay, well, that's something I'm personally interested in currently is verified MCMC. I can't say that I'm close to doing that, but I don't know, to be honest. Hopefully, we can at least make it that far to verifying kind of basic Metropolis Hastings. That would be interesting.
Cool, thanks.
Does your development assume any axioms, in
Yes.
particular in the correspondence to the algebraic CPOs?
Oh, I mean, yeah, so we use some non-constructive axioms. Throughout the development, we use a non-constructive supremum operator that is derived from, derived from a weird axiom called, what is it called? Indefinite description.
Yeah.
And excluded middle. We use excluded middle.
Okay.
And so, yeah, that really makes things a lot more ergonomic.
Okay, but you don't assume anything beyond those about like the coinductive trees?
We may have an extensionality axiom on one of these, the types that we use. It's in the diagram, it's called co-trees. I didn't talk about it.
Yeah.
So yeah, we use, for coinductive types, you don't really have regular Leibniz equality in Coq, and so we assume an extensionality axiom there to make that easier as well.
Okay. Did you think about, instead of using I-trees, using the limit of finite approximations representation directly and trying to set up a way of doing extraction from that?
Yeah, I've thought about that. There's a performance problem, though. I mean, if you do that in the most naive way, then like moving from the nth approximation to the n plus 1th approximation involves like recomputing the entire thing up to that point. And so, I mean, at least that way wouldn't really work. So my experience is that kind of representation can be useful for reasoning, and that's kind of why we have this auxiliary type of co-trees. It's like we have a separation between the constructive realm and the sort of ethereal realm of these things that we're just purely reasoning about but not extracting.
Okay, thank you.
Okay, let's thank the speaker again.